Thank you for great introduce. I'm Andrii Cheilytko, and I'm working DLR. And why I'm here? Yeah, DLR, German Aerospace Center, Institute of Solar Research, and how it's can connect with cement production. Maybe it's first question. So my talk will be about three parts. And first part, I'm little bit explain what the solar research and in German Aerospace we do. And our Institute of Solar Research include in general first, okay. In general, German Aerospace Center take care about aeronautics, space, energy, traffic, security, defense, and digitalization in whole Germany, and we are part of ESA Center, if you know. Energy research, it's first of all, it's controllable sustainable energy system. We use it different source as wind turbines, concentrated solar system, and transduced memory and technology. We can demand heat energy, electro energy, included householder, mobility, and for industry system in general. We provide power and heat. We can create fuels, solar, hydrogen, and others now. We also management and working with management and digitalization. Now about Solar Institute. So, solar is the biggest potential source in our planet. Maybe in Mercury or Mars we can others. But for our planet, it's not comparable. In the slide you can see it's for potential. What's the potential energy we can have? Question, why we don't use it? Or use it but don't enough? If we compare with fossil fuels, you can see, and included with biomass, it's not comparable in general. But what we use in time for 2020, energy sources use it worldwide. Almost 80% we use fossil fuels. It's fact. Use it. Little bit nuclear. 7% biomass. And 11% of renewables energy. Question, with this biggest potential, why we don't use it? What the problem is? With low cost or with not enough scientific research or with not enough energy efficiency? So, yeah. Our institute is about future. We thinking how we can improving currently technology in every industry, in every householder, and how we can use our solar energy for any technology. Our institute have different departments. It's concentrating solar technologies. It's about quality assurance and operation optimization for solar power plants and photovoltaic system, agri-photovoltaic, solar energy meteorology, and heat transition energy building assessment. What's the concentration? Today we must speak about concentration technology and how we can use this concentration technology, solar concentration. It's for the most common technology. We speak about two uses. It's parabolic trough and solar tower. The general principle of work you can see in the slide. We have some reflector mirrors that collect our solar rays and bundle it and reflect to the solar receiver. Solar receiver, it's different kinds. We can design a lot of kind solar receiver, and but main task of solar receiver is transfer our radiation to heat energy, and after we can use this heat energy for other system. It's including with catalytic reaction or without catalytic reaction. A little bit more about how it's work for solar tower. Why solar tower? I'm working. So we have a lot of heliostats. It's field of heliostat that collect bundle our solar rays and reflect to up of solar tower. One moment, and yeah, and collect to up in solar tower. In solar tower we have solar receiver. In solar receiver we have transfer our radiation energy to heat energy, and usually we use it to thermal storage, hot tank and cold tank. This schema is for molten salt. We use it molten salt, and due a heat exchanger we can transfer our energy to steam, to water, and it's this part is standard part of thermal power plant. So we use steam for turbine, 2-3 stage of turbine, high pressure turbine, low pressure turbine. For solar tower, it's usually we use low pressure turbine, and with turbine we can and electro generator we can produce the energy, electro energy. Other way, we can use air, not molten salt. Why air? Air have so a molten salt we can use only maximum for 545. Okay, now it's 75 degree of Celsius. With air we can heat up air for 1000 degree, and we do it 900. Okay. So with we use it for this technology open volumetric receiver it's called, and we heat up air with have some storage for air, and use it hot air for or heat exchanger and generator our steam and for transfer energy to steam, or we can use it from this scheme to cement production or other technology. We have high temperature fluid. In right side, it's 2 solar tower, our building. This spot is for air. It's open volumetric receiver. Other tower we speak in other slide about other tower. So what is the technology have? What the advantages this technology have? CO2 free, of course. Sustainable energy, of course. 24/7, yes. Theoretically, potential we can get it with big tests, thermal energy storage. Theoretically, practically, no. It's low efficiency. Adjustable, yes. Hybrid power plants with PV, it's possible. So for product electro energy or for complicated, we spoke about cement technology, it's also possible create hybrid power plant. So we use it concentrator our parabolic troughs or solar tower with PV panel. And for last research, we have low cost, where it's near be low cost only with PV power, PV panel. So it's very have very good economically profitability. but we have and electricity and heat, not only electricity. So it's also possible to use for district heat network, can provide process heat of industrial plants and without rare sources. And we used it in Germany. Come on. We haven't solar in Germany. It's like, it's not solar day. It's not, okay, Stuttgart may be more solar country. We, in NRV, North Rhine-Westphalia region, it's near Köln. It's like, it's not solar. It's not about solar in general. It's more weather as in Netherlands. So, milestones of our institute. We started in 2011 with some parabolic throws and some facility in Köln. I think it's, yeah. Institute, it was found Institute of Solar Research, not about aeronautic, but about solar energy and sustainable energy. In this year, we also take over of the Jülich Solar Tower. It was a real product for electric producing, and yeah, we bought it. In 2017, we built in sunlight the biggest artificial solar. It's a powerful laboratory for solar research. In 2020, spin-off from us, it's and created was established Institute of Future Fuel. It's solar hydrogen, solar kerosene, and others, solar gasoline. And 2020, it's we built second building, second solar tower for research. It's multifocus solar tower for research particle receivers, for cement technology, and others technology. It's possible to provide. Our geolocation. The main for solar tower we have in Jülich, North Rhine-Westphalia region. Parabolic throws and facility we have in Köln. We have a solar power plant in Spain, Almeria. And in Stuttgart, it's research center for fluid dynamics and material technology. Okay, what we do. Department for Development and Optimization for Solar Thermal Power Plants. Included solar high temperature technologies, solar power plant technologies, qualification, and chairs in Aachen. Department Solar High Temperature Technology. It's a fluid system, particle system, and modeling of system. Department Solar Power Plant Technology. It's simulation and open volumetric receivers and Jülich Solar Tower Plan, included engineer task and engineer group. Department of Qualification, System Qualification, Solar Energy Meteorology, Materials, Layers, Components, including mirrors, glues, and others, and building and quartz. Our facilities. Platforma Solar Almeria, Spain. Operator CMAT. Process heat test facilities, Köln, Germany. Evora molten salt platform. Jülich experimental solar tower plant. 2000 mirrors. Our spin-off, it's CCP service, it's Heliocon, it's Heliostat, it's Lumina. It's lot of other company, and it's not included last. It's down. It's first in the world solar kerosene production. It's manufacturing for solar kerosene production. It's our spin-off. And little bit Institute of Future Fuel, because they will be spoke about in speak about it in a third part. Institute of Future Fuels research also about calcination process directly solar radiation. So it's about our institute, our technology. Shortly, I know the time of lunch, but I have little bit time, so I'm try to spend it for more scientifically. Second part of my talk, it's about heat mass transfer, and it's for student researcher who interested in absorbance technology, porous technology. My ground it's heat mass transfer in porous media in general, and since 3 years it's I have focus for solar absorbers. So we have one moment, please. Good. So, theory of heat mass transfer process is solar absorber. First of all, I understand the good chemistry, civil engineering, and others. But I'm think and I hope then you know a little bit about heat mass transfer. Yeah. So at least we have what the kind of heat transfer we know. So we can transfer energy due to the radiation, due to convective and conductive. And of course diffusion. It's mass transfer. What's the question we have? First of all, for porous structures, we have a lot of methodology, but the common method is numerical. What's the problem with numerical? We can calculate it with numerical almost everything. But question, can we optimize structure or can't with numerical? Yes, we with one materials and 1,000 operation have 1,000 result. We can optimize some porous structure if we want get structural structure. Question, can we do it with analytical way? With analytical mathematical way, it's very easy to do. No, right now, no, we haven't. We haven't good enough quality of analytical approach. And it's my task create this approach or improving currently approach heat mass transfer. What the problem is, so we have some method. The most common, most easily method and use some efficient coefficient. In standard equation, we use it S, it's solid, F, it's fluid index. So we use it some standard Fourier equation for calculated heat transfer process with sources or without sources. For first approach it doesn't matter. We have some structure like this. It's have some fluid, they'll go due at this structure, doesn't matter boundary conditions, and we can use it for first solid thermal conductivity and alpha. First question is how calculate. So this is quality enough if we use it only solid and fluid like this or not. not enough. Second question, whether we can use alpha dual Nusselt. Of course, we can use Nusselt criteria for calculation alpha. What's the equation for calculation Nusselt? Typical equation like I will speak about it and show. Typical equation? No, it's also not good enough. So 30% we have accuracy in calculation alpha. It's the best that I can find for some structure that we know. Unknown structure, we have more than 100% accuracy. It's not research accuracy. So, we thinking how it's different shape have influence for thermal conductivity. First, it's without some convectivity, just conductivity coefficient. We can see that it's some shape of this pore have influence. After we just can, it's very simple experiment for the student with borosilicate glass, and we know porosity, we can measure it. It's very easy for thermal conductivity, and compare with different fluid. We can have the most popular Aiken, Schutz, Torkar. It's it's about Odilevsky, Heat Atlas. It's I'm not sure. You use Heat Atlas in India? It's like it's the most popular engineering book for calculation everything for heat mass transfer in Germany, but yeah. So and standard singly packed backfill loose packet, and we can have our experiment point. You can see some others equation. Yeah, we have two. So it's our DLR. It's about next slide, and it's about in Heat Atlas very closely. We can calculate it only efficiency. It's only one coefficient, and it's for chaotic structures that I think you will be used in your receiver. So I not will be spend your time, lunchtime, for methodology and very deep approach. It's we included some coefficients that can, as a dislocation vector, this coefficient included some geometry characteristic our structure, and after we included this coefficient, we can get with analytical approach some solution for different structure, as for chaotic structure as a form, and for LTE model included, and for catalysator also. So this model have as less than 10% accuracy. It's better for our task, good enough. For other, I'm not sure. But for solar research, because we have the biggest transfer energy due as a fluid, due as a convective transfer, we 10% for conductive is good enough for us. So we can, in this slide, you can see comparison of different models for calculation of effective coefficient thermal conductivity. This is part of absorber type heat rack. This is part of absorber type step rack. 3D model, 3D printing. This is absorber. It's due to 3D printing. This is silicon carbon. So theoretically, we have two standard curves. Between this curve, it's our real solution. So, and you can see that with proposed our model, it's theoretically good. And practically, we included this module in standard approach as a homogeneous approach for in open form and calculated our heat transfer. I can see very good accuracy. But it's about, so we solve only one problem like 2 years ago. Second problem, it's about conductivity transfer, heat transfer. And you can see in this slide, standard graphic, Nusselt from Reynolds. And you can see different theoretically function. This is numerical solution, and around its experiment. And what's the problem with this? Coefficient, Nusselt coefficient, we can calculate, due to Nusselt coefficient, we can calculate alpha. Yeah, of course. But Nusselt coefficient, we can calculate only for some simple structure of absorber. Or we use it for chaotic structure, we can use Darcy equation. But it's also not better result. So, what's the problem with create some, do some experiment, measuring it's all, is said, okay, it's working, we know for this. Problem is that if you change little bit other parameters of structure, or fluid, or angle of solar radiation, your model not be working. So you can't just do experiment and say, okay, I'm use this coefficient for others my model. It's not working, unfortunately. Standard way, yeah, it's including its standard way, standard book of heat mass transfer theory. We can calculate the coefficient C, N, and M if we know Reynolds and Prandtl coefficient. It's we build some graph. We have experiment with some point and building this line, and after this we know angle and can calculate our others coefficient. It's standard way for understand with experiment Nusselt criteria. Yeah. But if we have, this is one channel for its new absorber for solar radiation with 3D printing technology. This is one channel, like this schematic. We have 5 sections. In each section have different geometry parameters. And each section have own solution for standard Nusselt approach. If we will use standard. And yeah, and first section in general, not it's like we can see that it's in general impossible create one curve for understand our coefficient. Yeah, this is our fluid dynamics model, and it's like look this absorber in full model. So we think about different how it's possible to create, and like half years ago we published article, and we can create universal model for different approach. It's standard, the most common, most popular solar absorbers for open volumetric receiver for air, heating air. So it's heat rack 2, it's step rack 2, and EMI rack. It's one channel of this absorber. you can see on the slide. And for each absorber, we have standard model. That standard model, it's very average. Yes, good, but it's not, we can't with standard model, it's not changes with our Reynolds. So but we know if we change our velocity of fluid, it's of course our heat mass transfer will be increased. So we calculate with our proposal equation and can compare with numerical solution. It's closely better than previous, but equation is looking like very big, very scram. It's not simple, but in general, it's one line in program. Yeah. So we can use Python for programming, for calculation, analytical, for thermal balance, energy balance, and it's one line. So most important that we created this equation, and with this equation, it's included a lot of different parameters. But if we know what the geometry parameter we have, we can calculate it Nusselt criteria. And we can do task optimization, the most important with this equation. So we can find optimal structure. If we want to maximize Nusselt, we can find, as an example, equivalent of diameter of the channel. It's of result for validation. It's good enough. And conclusion. Conclusion, now we have previous equation. It's also, as a universal model, it's 20-25% accuracy. It's not always enough, but it's better that we have previous. Right now we have, as a scientist, task and adjustment. Scientist task, we have improving and finalizing with radiation model this analytical approach, because right now we have different two radiation model, and we have a lot of engineering tasks. For practical, I'm included this slide. It's about particle, because I'm not included particle receiver and how we calculate particle receiver, particle heat mass transfer. Correct, it's heat mass transfer in particle receiver. We can calculate using heat transfer. It's standard equation. We can calculate it, and it's work, and very good accuracy with experiment. So I have little bit time. So now about how it's work in practical, because theory it's interesting. First of all, it's already was talking about cement production, and you know it's better than me what's the currently situation in the world with cement. I'm also can add that solar energy, it's not only possible use, it's need to use. We can use, in this slide, it's you can see two configuration of rotated tracker for clinker. So it's directly irradiation. We have solar rays inside. This is rotating part. Solar rays go inside here. It's principle we can separate two technology, open and close. With purge gas flow can be injected at the windows and through suction can be applied at the back and open configuration without glass, where suction can be applied before and behind the aperture. In our laboratory, it's looking like this. We have we had some experiment with the limestone for calcination process. It's we can do temperature with this reactor. It's 1000 degrees of Celsius. It's for calcination, curved wave, insulation, crackable. Oh, okay. So it is experiment from our partners, Future Fuels. So before I spoke about how we can heat up some fluid. Now it's how we can use the solar energy directly. This is different. And for your project, I think it's you need to understand and what way you will use. Yeah? So calcination of cement rough material. It's 70 runs with calcination rates up to 95%. There is continuous mass flow from 4 to up 12 to 20 kilogram by hour. Heat input shows radiation up to 14 kilowatt. Investigation of mixed and heat up. You can look with these links. I'm leave presentation, and you can look this with these links, articles and results of experiment. I'm not be speak about it more detail. Calcination of kaolin and halloysine. We also did it and have some result with rotatory clean. Calcination of limestone. It's also part of our research. Calcination of kaolin included. And in this slide, you can find the phone and email from guys who responsibility for created this rotated fuzzer, and you can list him and speak. He said officially that he very want to new connection and want to speak with you. Yeah? So feel free to use it. It's from our partner. Now little bit for the end, I want to add a little bit how we can improve more temperature. If you need more temperature than 1000, we speak it, we can use air with temperature 800 degree. Already, we have this technology, can use it for mass production. We can use directly for 1000 degree of Celsius. Can use it. We have it. We get it. How if we need more? This is a question. We can use secondary concentrator. Secondary concentrator is concentrated nearby our whole two reactor. It's looked like this. And with secondary concentrator, we can additionally focus. So with this, we can use it more mirrors from long distance. More mirrors, it's more concentrated focus, and we can use for more radiation. And we can up to 1250 degrees Celsius. And little bit return to heat up air. It's our and we have discussed about need for heat up air. We need some mirrors or we don't need. Right now, we don't use mirrors, glass, about glass of reactor. We don't use glass with our receiver. So it's very similar shape. We have two absorbers materials. Usually this is ceramic absorbers. Second absorbers, it's from metal. We use it in Cornell 600 as a standard materials. Problem with that we have convection losses due as a boundary condition due as our buoyancy flow. Of course, we have gravity. We always have gravity. But we have thermal efficiency like we up the 90 degrees, 90%. Air return. Okay, air return. So we lose only like 10%, and we decide that it's better than we will be lose concentrated radiation in the glass. Because if we speak about small experiment and 1 megawatt, it's 1 point. But if we speak about 10 megawatt, absorption of glass is biggest than we will be lose due as the convective losses. It's also last point, and I was what about I want to talk. So, thank you.